In this lecture on working with data, we will focus on missing data. Turning our attention to a new topic, let's talk about missing data. Missing data are common, especially in survey research, online research, longitudinal designs, and um, generally in the kind of research that we conduct where we test humans who often refuse or make a mistake, what have you, and they produce missing data. Missing data are a problem when the missing values are selective and biased, essentially meaning that the missing data are missing for a reason, such as the poorest performers refuse to be tested, or selective responding, where somebody may not want to answer a certain question because it might reveal something about them that they don't want you to know. So, under these circumstances, missing data is not a random process, but is one that is attached to characteristics of the subject or the participants, and that can create bias because if multiple people refuse to give you the data that you want and they have a certain characteristic about them, then you're losing that data and you don't know um, what the values would be for those selected participants. Another reason missing data can be a problem is when the missing values account for a large portion of the data set. So if you're talking 20, 30% or more of the data is missing, that presents a problem. Missing values are likely to introduce bias that is be problematic when they're associated with any of the following. Poor health or cognitive impairments, where people may refuse testing or refuse to participate in certain parts of testing. Being either low or high income, where people may not want to reveal information about their income. Um, Being low education, people often don't want to participate and are selective in their participation. Concern over privacy issues, and I think that's a legitimate concern that many of us have today, and that would cause us to be reflexive in our responding and perhaps refuse to answer certain questions. And concern about appearances. We saw that in the 2016 presidential election, and I think I mentioned this previously, where polling indicated that uh, Hillary Clinton was likely to win the election, but in fact, we know that she did not win, at least in terms of um, the Electoral College. And that was because the polling was biased because people that they polled were not honest in their answers. Here we see evidence of the problems that missingness, biased missingness, can cause for conclusions. This is a study that I conducted and was published in 2005. And this is a longitudinal analysis of recall performance over age from age 70 up to an estimated 105. And what we see is that the participants that provided full data on all testing occasions are represented by the blue line. The green line is essentially taking those participants and adding back participants that had partial data, whereby we estimated through a process called multiple imputation the values that were missing. And we see that when we include the data of participants with missing data and we run the same analysis, we show a much greater rate of decline and also overall poorer performance. So this illustrates the problems that can be associated with having missing data that are not simply randomly lost, but are missing in this case because participants who failed to complete future testings following a baseline testing were more likely to have poorer performance.
So what are the different types of missing data, or what are the different states that missing data can have? Three different conditions have been identified. One is known as missing completely at random. A second is missing at random, and a third is missing not at random. These three different states, the names are a bit confusing, and because they may not mean to you what you would think they would mean. There are somewhat different definitions. Another point to make about these three states before I talk specifically about them and how they differ is that these are assumptions. These assumptions can be partially tested but not fully verified because all of the information that you need is not available to you to test the assumptions. And so that's why they are assumptions. Another point I want to make is that different kinds of studies are likely to have different amounts of missing data and are more or less likely to fit one of these three conditions. So, for example, in a typical survey or a correlational study or an experiment, the amount of missing data that you're likely to have is probably going to be limited, perhaps less than 10% of the total data will be missing, and that would be fairly typical. However, in other kinds of studies, such as longitudinal studies where you're testing people on multiple occasions over time, the amount of missing data grows with each testing occasion and can be considerable. And so it's that kind of study that requires a highly thoughtful approach to working with missing data. So of the three states, the first state, missing completely at random, is the easiest to deal with because there is no bias associated with missing data. That is, missing completely at random, MCAR, occurs when the missing observations are a random subset of the observations collected. That is, the missing and observed values will have similar distributions. This means that the missing data are not related to other variables, uncorrelated, and the missing values are unrelated to the variable itself. And so there is simply no bias. One way to think about this is if you have your hypothetical distribution of scores, and then you have your distribution of missing scores, which again is also hypothetical. The distribution of the missing scores should look like and be similar to the original distribution of scores. Examples of missing completely at random include when a participant brain farts a response, that is, they simply just make a random error, perhaps missing a question, or when the experimenter fails to record a response or loses the response, something like that. So truly random occurrences that cause missing data. For missing completely at random, for data that fit this assumption, any missing data treatment that does not add bias, such as mean substitution, is okay to use. The next assumption is missing at random. And this assumption essentially suggests that while you have missing data, that missingness is not random, but you have variables that can predict the missing scores. So the definition is missing at random, MAR, means that there might be systematic differences between the missing and observed values, but these can be entirely explained by other observed values. And so the key here is the word entirely explained. What that suggests is that the missing values are predictable from variables that you have data on. So, for example, in terms of aging, it is often the case that when somebody refuses a test, they're likely to be older than people who don't refuse a test, and that could be because they are cognitively failing or have some physical issues, and so this would mean that age is a predictor for the values of that missing test. This is sometimes referred to as ignorable non-response or ignorable attrition bias, and this means that the data can be predicted by other variables in the data set. In a study of depression, for example, participants with higher levels of anxiety may refuse to complete the measure of depression and so that is the cause of missing data. So because you have that measure of anxiety, that would allow you to predict the missing values on depression. Missing data treatments that make use of information from correlated variables are appropriate. And so those would include single imputation, which will be discussed in some detail. That's not the best of the possible treatments. Another one is multiple imputation. That's a variation on single imputation that uses information from correlated variables to predict the variables, or finds similar cases and imputes the value from that case. And then the third treatment that is viable is something called use of the FIML algorithm to fit a model to the data. And we'll talk about this rather magical technique at a later point. So the third state of that missing data can have is known as missing not at random. And this state, MNAR, relies on the fact that the data are missing is systematically related to the unobserved data. That is, the missingness is related to events or factors which are not measured by the researcher. And this can occur in two different ways. For example, it can occur because the missing data is associated with the levels or the values of the variable that has the missing data. So, for example, greater depression in a participant may be associated with non-response on a measure of depression. In that instance, it would be impossible to know what that value is because you actually can't measure the amount of bias because you don't have anything that correlates with the measure of depression. You simply have missing values. You could perhaps make the theoretical assumption, but it is untestable. Another way in which missing not at random can occur is when the variables that might correlate with the variable that has missing data that would allow you to make the assumption of MAR, missing at random, because you could predict the missing values when those variables are not measured. That is, you're not collecting data on variables that could be used to help impute the missing values on a particular variable. And so, for example, let's say that health predicts scores on, or could be used to predict missing values for memory performance test, but you didn't measure health. Therefore, you don't have the variable that could help you predict those missing values. Of the missing data treatments discussed here, MI and FIML may be helpful to the degree that there is any level of prediction, but the sad truth is there is not much to do to reduce bias. So let me just conclude then by saying that missing not at random is a state of missing data that really introduces bias. There is systematic bias in the missing values, but you really don't have any way of fixing or removing that bias. And so that is a perilous state.
In the next several slides, I will demonstrate the three different states of missingness: missing completely at random, missing at random, and missing not at random. In the next two slides, the one you see in the following slide, I demonstrate missing completely at random. So looking at this data set, we have 6 participants shown, but there's actually 160 participants in the data set. And we have data for the following variables: age, vocabulary, shortened version of a vocabulary test, education, the number of years of education a person has, their sex, recall at time 1, recall performance at time 2, and then a missing data identifier, referred to as MISDAT. So the variable that is going to have data pulled from it is recall 2, and that variable is highlighted in gray. So if we were to remove three values from that we see where the arrows are pointing to, and we did that in a completely random fashion, then that would potentially meet the criteria of missing completely at random. And in the next slide, so now we see that the three values have been randomly selected and removed. Note that the mean of 8.26 is actually the same as the mean in the previous slide. The randomly removing data should not affect the mean very much, especially when you have 126 cases. So that would be an example of missing completely at random, and it's not going to affect the mean or measures of variability, etc. In the next two slides, I'm going to demonstrate the missing at random assumption. Here, I'm selecting among the poorest performers, and I'm going to remove their scores. This might occur because those people know that they're not likely to do very well, and they don't want to be tested, so they refuse to be tested. We don't get their recall at time to score. So in the next slide, you'll see that those values are removed. Pay attention to both the sample size n of 160, which is going to get smaller, and most importantly, what happens to the mean. It's going to change from 8.625 to a new value. So we've removed the people who would have performed most poorly because they theoretically refuse to participate. And so now our sample size is reduced. It's now 126. Most importantly, the mean for recall 2 has gone bigger. And that is a problem. That represents that the missing data are missing in a biased fashion that is changing some of the fundamental descriptive statistics that we obtain. However, we can assume the missing at random assumption because if you look at the far left side of the slide, I have a set of correlations, the different variables and their correlations with recall at time 2. And so we see that age correlates at 0.3 with recall at time 2. Vocabulary, education, and recall at time 1 all correlate with recall at time 2, as does a missing value identifier, missdat. All of these variables correlate with the variable that has the missing data, and that implies that we can estimate the missing scores. Because we can estimate the missing scores, we can get rid of much of the bias that exists, and this is known as missing at random. Now let's focus on a situation that would be defined as missing not at random. This is a situation in which the scores that are missing in a biased fashion. In this case, the poorest performers do not contribute data to recall 2, and we again see that inflated mean of 9.23. When we look over at the correlations between recall and age, vocabulary, education, recall at time 1, and missing data, we see that the correlations are all 0. That would indicate that we cannot predict the missing values. And that means that the missing data are missing not at random, MNAR. So how do I know if my missing data is missing completely at random? One indicator is Little's test of MCAR, where essentially this is a test where we can request, or that we can request from SPSS through a particular program known as missing value analysis. And in Little's test, if Little's test is non-significant, then the data are assumed to be missing completely at random. So essentially the test evaluates patterns of missing data in the variables and looks for associations in those patterns. If it finds none, and it doesn't find evidence of bias and missingness, then it computes a value, a chi-square value. And if that chi-square value is non-significant, then we assume MCAR. If it is significant, then we cannot assume MCAR. Therefore, the data would either be missing at random or missing not at random. And of course, we would hope that the data are missing at random because that would allow us to estimate the missing values. If Little's test is confirmed that the data are missing completely at random, then we don't worry about attrition bias. We simply have to decide what we want to do with our missing data, and I'll talk about that in a few minutes. So how do I know if the missing data are missing at random? Well, first, assuming that we run Little's test, and it indicates that the data are not missing completely at random, then we would assume that they're either missing at random or missing not at random. And of course, we hope that they're missing at random because that means we can do something to correct the problem. So once we've looked at Little's test, then we would run some correlation matrices. And if we find relationships between the variables in the data set and the variables with missing data, that would indicate MAR. That would be support for the missing at random assumption. In addition, if we conduct analyses that correlate the variable with missing data with a new variable that we compute, a missing value indicator, and that variable has a correlation, then that would indicate also that the missingness is, that would indicate bias in missingness. But because variables exist to estimate the missing data, we can assume MCAR. If those other variables do not correlate with the variable that has missing data, then we cannot assume MAR, and we are forced to assume uh, that the data are missing not at random, that essentially means there's nothing we can do to fix the missing values. In the next slides, I describe 5 different treatments for missing data, and they are listwise deletion, mean substitution, single imputation, multiple imputation, and use of the FIML or ML algorithm in certain kinds of statistics. So those are the 5 methods that I will describe in some detail in the following slides. Listwise deletion eliminates an entire case uh, that is associated with missing data on a variable of interest, variables that we are going to include in our analyses. So the result of using listwise deletion means that we are going to have a complete cases data set where there is no missing data. And that's a good thing. However, listwise deletion reduces sample size and in doing so reduces power, the power to detect differences or effects. So listwise deletion is probably the easiest approach, but it does nothing to get rid of attrition bias. So it really should only be used when we know that the missing data is missing completely at random, or if there simply isn't very much missing data, let's say less than 10% of our data is missing. Let me emphasize that listwise deletion reduces sample size, and that reduces our ability to detect the differences or associations that we hypothesize. That may mean that we would need to run more participants. It also is a situation where we are getting rid of people who have, with a few exceptions, perhaps given us their valid data. And so generally, I discourage against listwise deletion unless the amount of data is relatively trivial. The second approach to treating missing data is known as mean substitution, and that essentially replaces the missing values with the group mean or other measures of central tendency. So, for example, in SPSS MVA, they provide several different approaches to doing mean substitution. However, generally, I would recommend against using mean substitution because not only does it retain bias, but it inflates any bias. Why does it inflate or contribute to bias? When we replace missing values with the mean, that means that we are going to reduce variability because we're trending uh, the mean to be a stronger effect. And we've got fewer scores that um, vary from the mean. So we'd reduce our estimate of variance and the standard deviation. And that is really not a good thing to do. Also, we retain all of the bias that's there, so we're not in any way fixing any bias in missingness. So what I would say is do not use mean substitution unless your missingness is missing completely at random, or you have less than 10% of the data file that has missing data. But generally, don't I don't think this is a good approach because it reduces variability in scores. It inflates bias. The third approach to treating missing data is known as single imputation, and this replaces missing values with predicted values. So this is an improvement over both mean substitution and listwise deletion. Why, you might ask? Because we are using information that we have to predict the missing scores. And so this is a uh, often referred to as a considered approach to treating missing data. However, it should only be used when missingness is missing completely at random or missing at random. There are two methods that are often used for treating or estimating the missing values. Essentially a multiple regression method that's sometimes referred to as ordinary least squares regression or OLS regression. Or the other approach is known as expectation maximization, which is also referred to as hot decking. And this essentially is an approach where we find another case, another person's data that is very similar to the data that has the missing value for, let's say, one variable. And we take the value for that case, the one that has the data and is similar, and we plug that value in. So single imputation essentially is an approach where we estimate the missing scores to better represent the data that we would have had if we had the data. The drawback to single imputation is that it does not compute proper standard errors. And I'll talk a bit more about this as we talk more about single imputation. So let's take a look at the multiple regression method for performing single imputation. The reason I'm doing this is not actually because it's the best approach, because most people would say that expectation maximization is the better approach for filling in missing data. But I'm going to do this because it nicely demonstrates how you go about estimating missing values in a considered way. So the multiple regression approach follows the following steps. One, we're going to determine the missing values for a variable and then use listwise deletion to delete those cases, any cases that have missing data. That gives us a complete cases data set. Using that complete cases data set, we're going to do step number 2, which is to run a multiple regression and note the regression coefficients, including the intercept and B weights. Step 3, we're going to use the regression equation that would be associated with the regression analysis that we did to compute the missing score, or the score for the missing data for one participant. Then in step 4, we're going to plug the estimated score and scores after we do this multiple times, into the original data file to fill out the data set. So step one is on the next slide. In step one, I'm going to create a complete cases data set by removing the 3 cases that have missing data for recall 2, recall at time 2. That would reduce the sample size, but it gives me a data set that can be analyzed using multiple regression. In SPSS and most other statistical programs, you cannot analyze any cases that have missing data. So we have to create this complete cases data set. The next slide will show steps 2 and 3. So using the complete cases data set, we're going to run a multiple regression and note the regression coefficients. That step is done in the output box that we see on the right-hand side of the slide, kind of in the middle, where you see the output for a multiple regression, whereby we predicted recall score at time 2 from age, vocabulary, education, sex, and recall at time 1. And from that, we get the what are known as B weights, including the constant, which is also known as the intercept, and then the B weights for age, vocabulary, education, sex, and recall. And those are circled in a red square. Then to compute step number 3, we create the regression equation that is associated with this analysis. And so if we look at the third line from the bottom, you see missing recall 2 score is equal to the intercept plus the B weight for recall times recall plus the B weight for age times age plus the B weight for education times education plus the B weight for sex times sex, and finally the B weight for vocabulary times a vocabulary score. So we take the values in the red box, the coefficients, and we plug those constants into the regression equation. So the intercept is 9.545. That would be the beta sub I, or I'm sorry, the B weight sub I. That would be the intercept. Then for recall, that B weight was 0.595. Plug that in. Do minus 0.144 for age, and so forth. Then in the next stage of step 3, we note the person who we want to estimate their recall score at time 2. We note their scores. So their recall score was 7 at time 1. They were 80 years old. They had an education of 6. They were, I believe, a male. Vocabulary of 5, and we don't know what the recall score is. But we plug the values in, so recall of 7 gets plugged into recall 1 in the bottom equation. Age of 80 gets plugged in where age was. Education of 6 gets plugged in, and so forth. Now we have numbers for all aspects of the equation, we can solve the equation and we come up with a score of 2.371. So now that we have solved the regression equation, we have predicted the recall at time 2 score for participant 2. We can plug that value in, and we've then solved that one participant's resolved our predicted score. We would then have to do that for participants 3 and 5. Once we have, which would be repeating steps 3 2 more times using different uh, um, uh, variable values associated with participants 3 and 5. Once we do that, then we have we have imputed the missing data for recall at time 2. So that is a demonstration of how you could use multiple regression to estimate the missing values. If you do that using SPSS software, actually, I'm sorry, SPSS doesn't provide single imputation, but other programs do. If you did that, it would do all of this automatically for you. You don't have to do a thing. So we've seen how you could use multiple regression to fill in missing values in a data set. However, most statisticians would recommend not using the approach that I demonstrated. I only did that because I think it illustrates how you could estimate the missing values. But instead, they would recommend expectation maximization, also known as EM or hot decking. And essentially, what this does is it finds similar but valid cases to the cases that have missing data. By similar, it finds one or more cases that have similar values on other variables. And then it randomly selects from those similar cases the value that it will, one of those cases, and then it will take the valid value and use that to fill in the missing data. Expectation maximization is valid if the missing at completely at random assumption can be made, and it is by far the best missing data treatment discussed so far. This may actually be the approach that I would recommend that many of you use for your thesis data. But there are better approaches that can be used, and we'll talk about those in a few minutes. By the way, SPSS allows you to do this in the missing value analysis plugin. The expectation maximization approach to treating missing data can be performed in SPSS by going to the analysis pull-down menu and opening up the missing value analysis tab. This will allow you to do three things. The first is to describe the pattern of missing data, including the following. determine where the missing values are located, how extensive they are, and are the missing values, do they fit the MCAR assumption? So that's the first uh, information that you can get from MVA. Secondly, upon request, MVA will estimate the mean, standard deviations, covariances, and correlations for different missing data methods. Essentially, what this will do is tell you what the mean, for example, would be if you use a particular method. Um, and you could compare that mean to the complete cases mean to see how the particular treatment of missing data is affecting the mean and other statistics. Um, and you can do this for listwise deletion, regression-based single imputation, and expectation maximization. Again, in this case, single imputation. The third thing that you can do with the missing value analysis is essentially impute the missing values. You have to request that they be imputed by checking a button. And essentially what this will do is create a new data set that imputes the missing values. So you'll see when you compare the original data set and the imputed data set, you'll see that values have been inserted. Those estimated values will have been inserted where the blanks were. This is an example of the missing value analysis menu, and we will spend some time in class working with MVA and exploring some of the things that we can do with it. And here is an example of Little's MCAR test, which in this case is non-significant. So that would mean that the MCAR assumption, the missing completely at random assumption, is supported. Therefore, virtually any of the missing data treatments that I mentioned are reasonable, although I do want to re-emphasize that single imputation would be the best approach of the ones that I talked about. Listwise deletion is probably the next best approach, followed by, I think the poorest approach is mean substitution. Also in this output, we see what the means, the covariances, and the correlations would look like if we use expectation maximization to impute missing data. So at this point, we've talked about 3 different methods for treating missing data. And I just want to say that the best of the 3 that we've talked about at this point is single imputation with using the expectation maximization approach to estimating missing data values. This can be used if the missing completely at random assumption can be made. Again, if you have less than 10% of your data that is missing. I have some links to YouTube videos on use of the expectation maximization imputation approach. So you may want to take a look at those. So expectation maximization is probably the best that we've talked about, but remember that strictly speaking, it is only appropriate when we can assume that the missing data are missing completely at random. In the next slides, I'm going to talk about two approaches that are considered to be equally valid for treating missing data when the assumption that we have to make is not missing completely at random, but rather is missing at random. So the first approach to treating missing data values, when we can make the MAR assumption, the missing at random, but MCAR is violated, is multiple imputation. Multiple imputation is like single imputation, but it estimates values in more than one data set. That is, it estimates values in M greater than one data sets where M is a data set. And it does this because each time it estimates a value for a missing data point, it does so with slightly different values imputed in each of the data sets. So what this means is that we're acknowledging that the data point that is imputed is not likely to be the exact data point that should have been imputed. That is, we're acknowledging through multiple imputation that there is error in our estimate of what value should be imputed. So by imputing more than one value, we essentially acknowledge this problem and between data sets essentially create error associated with our best estimate of the imputed value. And I'll talk a little bit more about that as we continue. So the estimation procedures that are available for multiple imputation are the same as the ones that are available for single imputation. That is, multiple regression can be used, sometimes known as the predictive model, or expectation maximization can be used. And again, like single imputation, um, uh, uh, the better of the two is largely considered to be the expectation maximization approach. So once we impute the missing values, then we have M data sets, which is usually between 3 and 5 data sets. Each of those data sets is analyzed separately. So if you're going to run a multiple regression, ultimately you would run 5 multiple regressions if you had 5 data sets. And then there are procedures for collapsing the results so that ultimately you get one summary set of results. And we'll talk a little bit more about this. I also want to say that SPSS now has the ability to perform multiple imputation, and it's actually pretty straightforward. So you don't have to combine the data or the output from multiple analyses. SPSS will do this for you for most statistics, including the vast majority of statistics that you are likely to use. Multiple imputation was first proposed by Rubin in the 1970s, and it's been around for quite a while. It's caught on in the last, I would say, 15, 20 years. Essentially, multiple imputation corrects for problems of single imputation, and I essentially said this, but I'll say it again because I think it's important for you to understand. Multiple imputation creates M imputations, that is M data sets or more than one data set. And this is done to reflect uncertainty about which value to impute, meaning we don't know the exact value that we should impute, nor does any statistic. So essentially what the procedure does is it selects out a set of values that are generally reasonable, essentially fit within a set of confidence intervals, and then randomly selects among those values, plugging in one of the values in one of the data sets. Then it goes back and again randomly selects from those values, selecting out another value for the next data set, and so forth. Across data sets, we can estimate the error in predicting missing data values. That is, we can get an estimate of the error in our prediction because we have different values that we've imputed. If there is less error, it's likely to occur because we had a better sense of what that value should be. If we have wildly different values that we impute, that means that our prediction is not very strong, and that is reflected in the values that are imputed and can be estimated as a standard error, an error in our estimate. Um, So typically 3 to 5 data sets are sufficient, and I'll talk a little bit more about that and other aspects of multiple imputation on the next slides. Let's talk about combining the results from multiple imputation. So again, we're going to have results based on running analyses from 3 to 5 times on those 3 to 5 data sets. And this means that we're going to have multiple t-values if we run a t-test, or multiple ANOVAs if we run analysis of variance, and so forth. So for most statistics, all we do is we take the average of the 3 to 5 results, and that is our final statistic. But in computing standard errors, this is where complexity develops because we have the standard error associated with the different imputed values, and we have the standard error associated with the statistic that is fit itself. So there are 2 different contributions to the estimate of standard error, and this makes it more complex. You can't simply take the average. There are formulas for computing the standard error, and fortunately, some statistical programs do this for us, including SPSS. So if you perform multiple imputation in SPSS, it will compute all of the summary statistics, including the standard errors. Multiple imputation, like many of our statistics, carries general assumptions that need to be met. And if those assumptions are violated, then the imputed values may not be valid. Those assumptions are normality, that all variables need to be reasonably normally distributed. Variables are linear functions of other variables. That is, that this is a linear statistic. However, there are versions of multiple imputation that can be applied for nonlinear relationships, and so see Allison in 2002. Um, Fortunately, Schaefer, who has a book on missing data treatment, showed robustness to violations of normality for multiple imputations. So he shows that you can have reasonable violations of normality and still have well imputed values. So for multiple imputation and single imputation, the question arises, how do you choose the variables that you're going to use to estimate the missing data? Well, first, you want to choose all of the variables that have missing data. And you would want to choose those in such a way as having the variables with the most missing data uh, included after variables with the least amount of missing data. You also want to include all variables that correlate with the variables that have missing data. And you may also want to include, or you should also include, all of the variables that will be used in later analyses, even if they don't correlate with the variables that have missing data. And there has been discussion of the what's known as the kitchen sink approach, which is just throw everything in. I'm not sure I would recommend the kitchen sink approach, but I would essentially recommend using all of the variables for the three categories that I've listed, and that could be quite a few different variables. So I mentioned that typically multiple imputation is done such that values are estimated for between 3 and 5 data sets. Given that SPSS does this automatically for us, it doesn't really matter whether we have 3 or 5 data sets. SPSS will compute the summary statistics just as easily from 3 or 5. To be a little more accurate, is an estimate of efficiency. I'm not going to go specifically into that, but it exists so that if you want to know how many data sets you would want to estimate, that you can use this formula. Generally, I would recommend just going ahead and doing 5 data sets. You're probably pretty safe in making that selection. Today, many different statistical packages provide the means for performing multiple imputation, including SPSS, Stata, Solus, which is a software package designed specifically for performing missing data analysis and different imputation techniques. Norm, which is a shareware, free shareware program provided by Schaefer. ProcMI, which can be run in SAS. And finally, there are packages in R, including the mice package. And I'll give you a link for doing um, multiple imputation in R using mice. The advantages of multiple imputation is that it can be used for most all of the statistics that you are likely to want to utilize. And it creates actual data sets, which may not seem like an advantage at the moment, but the next data treatment that we're going to talk about, which is the FIML algorithm, does not create actual data sets. So that can be something of an advantage because then you have the extant data that you can analyze and also keep. The disadvantages are it is cumbersome, although having the ability to do this in programs like SPSS in a fairly straightforward manner makes this less of a problem. And it can result in different estimates for the same data depending on how different people apply the program. This is actually true in many different statistics and approaches where different people will do things in slightly different ways, which means that absolute replication of results is very difficult because we may make different choices along the way that would exclude data, these kinds of things. So, it, given a large data set with complex questions, you're likely to see somewhat different results across um, researchers. The last missing data treatment that I want to talk about is known as maximum likelihood, and it was proposed by Wertke in 2000. Well, it actually was around before 2000, but he's been one of the people who's really sold this idea of maximum likelihood. So it is a model-based estimation that adjusts the parameter estimates to account for missing data. So this approach does not replace missing values with actual numbers. Instead, it is an approach where the statistic that is being utilized can deal with missing data. And if you add in um, variables that are predictive of that missing data, the variables that would give you justification for the missing at random assumption, then use of the FIML fitting algorithm, by the way, sometimes also known as ML algorithm, uh, will estimate values that take into account uh, biased missingness. Um, and this can be done in structural equation modeling and multi-level modeling programs. It can also be done with other advanced, often latent variable statistics. Um, So the software for doing this kind of, or using this approach include AMOS, which we'll use in this class, MX, M+, SAS, HLM, which is hierarchical linear modeling, and R, among other programs. So just to reiterate, maximum likelihood, its approach to treating missing data, it does not include the actual imputation of estimates that are plugged into a data set. Rather, it gives the statistic the ability to estimate parameter values that are uh, altered to reduce bias for missing data. So in this slide, we see an example of the way that this might be done. Um, the, uh, the graphical user interface on the left is a structural equation model used to model longitudinal data, and it's called a growth curve model. And it includes, it's actually pretty simple. The actual data is in the rectangles, and that would be data at baseline, data at 1 year, data at 2 years, and then a fourth testing 3 years later. And then we have a parameter estimate for the intercept in the oval on the left, and a parameter estimate for the slope in the oval on the right. By running this model, if there happens to be missing data in year 1, year 2, and year 3, um, if we call into play something known as the full information maximum likelihood algorithm to perform the model estimation to compute the intercept and slope. Having these variables is likely to partially treat any missing values that exist in the data, assuming MAR, that is missing at random. In the model on the right-hand side, you'll note that additional variables have been added to predict the intercept and slope, and these include health, sex, age, and education. These variables would improve the estimation, assuming that they are predictive of missing values in the 1 year, 2 year, and 3 year data. They would improve the estimates of the intercept and slope, uh, helping to reduce attrition bias. So it's a little bit complex, but this is the way that missing data can be dealt with using the FIML algorithm. So at this point, we've talked about a variety of different methods for treating missing data, including listwise deletion, mean substitution, single imputation, multiple imputation, and use of the FIML algorithm when we use structural equation modeling or multi-level modeling. So which method should you choose? That depends on a number of things. For example, the percentage of missing data. If you have only a small percent of missing data, clearly less than 10%, use of any of the approaches that I've mentioned is not off the table. Although I do want to reemphasize that the use of mean substitution is bias inducing, and the use of listwise deletion reduces power. So you may want to avoid those, but they are in play if you have only a small percentage of data. If you have larger percentages of data, that's where single imputation and multiple imputation are useful. And if you're doing structural equation modeling or multi-level modeling, there may be no need to actually create the data sets. You can do it assuming that you include the missing data in the data file that you analyze, and as the estimator of the parameter estimates, you call in the full information maximum likelihood algorithm. And we'll talk more about this when we talk about SEM modeling. It depends on the processes that you are modeling and the statistics that you plan to use. So again, if you are doing structural equation modeling, perhaps a latent variable model, you would probably want to choose the FIM algorithm. For more traditional statistics, like analysis of variance, multiple regression, you're more likely to depend on imputation methods, either single or multiple imputation. There are disciplinary biases. So, for example, in developmental research, we're more likely to use, I think, the FIML algorithm than other approaches. Um, and generally speaking, the best approaches, the gold standard for the estimation of missing values is multiple imputation and the FIML algorithm. But many studies can utilize single imputation or listwise deletion. And for many studies, that's a reasonable thing to do. This slide provides references for uh, different sources on how to do missing data analysis. So that completes our discussion of uh, data management and included discussions of creating a data file with best practices, cleaning a data file of wrongly entered data, the identification and treatment of outliers, the identification and treatment of misshapen distributions, an extensive discussion of missing data treatments, and just finished up with a brief summary of the different statistical packages that are available.